Let's illustrate the central limit theorem with an example that's easy to recognize. First, let's remind ourselves about the central limit theorem, which essentially says this. Regardless of the underlying distribution, the distribution of sample means is approximated with a normal distribution, and that approximation gets better and better as the sample size increases. Let's use the example of rolling dice. First, let's consider the mean roll of one die. If we roll a single die, the options for what we see are the integers 1 through 6, and each of those realizations is equally likely to occur. What kind of distribution is that? Yes, a uniform distribution. So the population distribution is not a normal distribution. In fact, it's a discrete uniform distribution. And remember, we're taking the average of the dice rolls. If we roll one die, the average is just one value. If we roll 3 dice, a sample size of 3, we average the 3 integers that come up, and so on. Let's jump to Excel to see what happens. We're in Excel now, and we want to illustrate the sampling distribution, and in particular the central limit theorem, using the dice example. Okay? So what we're doing here is we are simulating several rolls of a die. Okay? And in particular, with one toss, we are just rolling one die. Okay? And we're taking the average of the result of that roll. Okay? So if we have just one roll, whenever you take the average of it, you're just getting that one value. So for example, what we're using here is the rand between function. Okay? Rand between function in Excel randomly chooses a number. It uses its own random number generator, which may not be the best random number generator out there. Okay? I've heard there's some problems. There's some research that suggests that the random number generator in Excel is not exactly random. However, for our purposes, it's good enough. Okay? So what the rand between function does is you provide it with a lower bound and an upper bound, and it randomly gives you back a value in between that lower bound and that upper bound. Okay? This is essentially a random number generator for a uniform, a discrete uniform distribution. Okay? And we've got 6 faces on a die, so naturally the possibilities that we could get back are 1 through 6. Okay, so we've got a lower bound of 1, upper bound of 6, each of which are equally likely to occur. Okay, so that's the implementation of a discrete uniform distribution in Excel. So for our first flip of the die, the first toss of the single die, we got a value of 2. Okay? In the second toss, we got a value of 1, and so on. And we ran the rand between function 10,000 times. Okay, so we ran this thing 10,000 times. We flipped, or we tossed one die 10,000 times, and we took the average of each one of those tosses. So we took the average of the one toss, okay, which is just the observation. Okay, but it's important to point out that it is the average of the sample size. So we took a sample of n equals 1 flips, and we took the average, and on that first average we got a 2. Okay? On the second sample of size 1, we took the average and got a 1, and so on. Okay? Then we created a histogram for these observations, and what do we get? We get something that looks like a uniform distribution, what we would expect it to. Roughly the same number of 1s were flipped on average as 2s, as 3s, as 4s, and so on. Okay? So this, for the most part works. We see a uniform distribution over these 10,000 flips, or 10,000 tosses of one die, n equals 1 die, whenever we took the average of the response. So now let's say we bump that up to n equals 2 and take the average. Okay? So instead of just flipping one, or tossing one coin, we toss 2. So here's one random number generation between 1 and 6, and another random number generation between 1 and 6. We have two die tosses, and then we take the average of the response. Okay? And what did we get? In this particular case, we got 5.5 for the average. Okay? We flipped 2, or we tossed 2 die again, and what did we get? We got an average of 5. We tossed 2 dice again, I should be saying dice, and we got an average of 3, and so on. Okay, so what happens whenever we see something like this? Okay, what happens whenever we increase our sample size from 1 to 2? Well, with 1 we saw a uniform distribution. With 2 we see something with a little bit more of a peak. And why is that? Well, there are a lot more ways to flip, there are a lot more ways to get an average of 3.5 than there are to get a 1, for example. What kind of toss would it take for 2 die such that the average would be 1? Well, you can only roll a 1 and a 1 to get an average of 1. How many ways are there to get an average of 1.5? Well, you could roll a 1 and a 2, or a 2 and a 1. Okay, so there are twice as many ways to get this average than there is this. What are the possibilities to get an average of 3.5 when you roll 2 dice? Let's see. You could roll a 2 and a 5, a 3 and a 4, a 4 and a 3, and a 5 and a 2. Okay? So you have a lot of different ways to get an average of a 3.5. So we see something that's not uniform when we increase the sample size from 1 to 2. Okay, what happens when we increase the sample size from 2 to 3? Same kind of idea. Okay, so now we've got a roll of a die, okay, once, twice, and 3 times. Okay, so we're rolling 3 die here, and whatever comes up, we're going to take the average of that. Okay, well, what happens? The first time we roll 3 die, we get an average of 2.33. Second time, we get an average of 3.67, and so on. What happens? Well, it becomes less and less likely that we're going to roll an average of a 1. How could you get an average of a 1? You'd have to roll a 1, a 1, and a 1. Okay? That's less likely than getting an average of a 3. There are a lot more ways to get an average of a 3 than there are a 1, and so on. Okay? So we start seeing a little more hump here. We start seeing a little more depleted tail on both sides. Okay, because these are getting less likely. You have to get very specific. You have to have very specific things to occur to get an average out in here in the tail. Let's now increase the sample size from n equals 3 to 5. What happens? Same kind of thing. So now we're rolling 5 different dice, and we're taking the average, and we are plotting that average on a histogram, and we see a little more pronounced looking bell shape, right? The tails are a lot more depleted. There's a lot more curvature up toward the peak. And then finally, let's say we took a sample size of 20. N equals 20. What happens? It looks even more like a normal distribution. Okay? And so on. So what we've seen here is we took a population distribution that was uniform. And as we increased the sample size, whenever we started taking the sample mean of n tosses, as n increased, we started seeing more of a normal distribution for the sample mean. Okay, this is a sampling distribution. That is a sampling distribution when the sample size is 1. This is a sampling distribution when the sample size is 2 and 3 and so on. And what are we seeing? As n increases, we get something that looks more and more like a normal distribution. Okay, and that's what we would expect to see based on the central limit theorem. What does the central limit theorem tell us? It says that regardless of what the population distribution is, regardless of what that thing is, that's a uniform distribution. Regardless of what the population distribution is, the sampling distribution, the distribution of the sample mean, starts to follow a normal distribution, and it gets more like a normal distribution as n increases. And we're seeing that exactly through our simulation of dice tosses.